So today we're going to be talking about differentials. Okay, so what is a differential? So when we've been dealing with functions and their derivatives, okay, so if I start off here with y equals f of x, when I take the derivative of y, I get dy over dx equals f prime of x, which makes sense because the derivative is basically slope. Okay, so when we think about the derivative, we think about slope, and dy is what we consider basically a small change in y, and dx is a small change in x, okay, which is also slope. But when we talk about the differential, we're talking about specifically dy is the differential of y and dx is the differential of x. So this right here, dy over dx, is a small change in y over a small change in x. But what if I only want to find how y is changing as x is changing? And that's what this equation basically tells me. It tells me, okay, based on how my x is changing, this is specifically how my y is changing. Okay? And these differentials are a way of approximating change in variables without having to actually do like y2 minus y1 to find the actual change. And it's faster sometimes because if you think about it, if your f of x is a really high power function, when you take a derivative, it lowers it by 1 power. So it makes it like an easier problem to deal with. This is also the idea behind linearization or linear approximation. Okay, and we'll talk about that more in just a minute. But just finding differentials is relatively easy. Okay, so for instance, the volume equation for a sphere. Okay, find the differential dv. Okay, so I'm going to take the derivative of this with respect to r. So when I take the derivative of v with respect to r, I get dv over dr equals 4 pi r squared. Just taking the derivative. Take 3, move it out front. 4 thirds times 3 is 4. Subtract 1 from the power, you get 2. So this is my derivative. This is telling me how my volume is changing over my radius, but I want just the differential dv. So you multiply both sides by dr, and you get your differential dv equals 4 pi r squared times, my board's not catching up with me, 4 pi r squared dr. Okay, and that's my differential dv. So this is going to tell me just how the volume's changing based on how my radius is changing. Okay, it's not going to give me the change in volume over the change in radius. It's just going to give me the change in volume. Okay, which if all I want to know about is the volume instead of the slope or rate of change, this is how you would look at it. Okay, and the same thing works for regular functions like this one. So I'm going to take the derivative of this one with respect to x. So you get dy over dx equals, and the derivative of this side with respect to x is 12x squared minus 6. But I just want the differential dy, so multiply both sides by dx. And so dy is 12x squared minus 6 times dx. And this should look familiar, like when we do integration by substitution and we're finding du, we're finding basically the differential du. Okay? We don't do that part where we take du over dx and then move the dx to the other side. We just do it automatically. Okay, but that's basically what we're doing is we're solving for the differential, and that's what we're doing here. So this is just finding the change in y. small change in y. Now, it's not actually delta y, and that's what we're about to talk about. Okay? So, if you remember, the tangent line equation, okay, and I wrote it a little bit differently. Normally, when we talk about the tangent line equation, we're talking about y minus y1 equals m times x minus x1, okay? But if you move y1 to the other side, you get y equals y1 plus m times x minus x1, okay? And the tangent line equation, this is the exact same thing. F of a is your y1, f prime of a, that's your slope, and a is your x1, okay? Now, so this is the tangent line equation. So say when we do linearization, where we linearize is basically here. This is telling me I'm taking the y value and I'm adding this part right here. Well, if x minus x1, this is basically a change in x. It's approximately change in x. It's actually, this is usually my dx. This whole part right here is dy, based on my equation that we just had. Dy is f prime of x times dx. So this is, when we do linearization, when we do tangent line approximations, this is basically my y value plus some little y value. And that's why this is an approximation. It's not actually change in y, it's an approximation. And that's what this shows you here. The actual change in y is actually this would be x1, so this would be, sorry, think of it more like slope. This is basically y2 minus y1. The actual delta y, this is your second value, it's a plus some change in x minus your original one. That's y2 minus y1, which is approximately this, the slope times a change in x. So think about it this way. If this is slope times delta x, right? Slope is change in y over change in x times change in x, so we're left with change in y. So this whole equation makes sense. Okay? So the actual change in y is y2 minus y1, but we can approximate the change by using the slope times my change in x, or my dx. Okay? So this is basically the use of my differential. So when I look at linearization equations, basically my tangent line equation is nothing more than y is equal to y1 plus dy. And of course, dy is, from our other one, f prime of x times dx. So that's basically what we're doing. So like when we do those square root problems, I mean, think about it in your head. When you approximated a square root problem in your head, like yesterday we did the square root of 38, okay? And we did a linear approximation to find the value. But in your head, you would say, okay, well, the square root of 38, that's a little more than the square root of 36. I know that that value is between 6 and 7. And 38 is closer to 36, which means it's probably 6.1 or 6.2, something closer to 6. That's basically what we're doing here. We're saying, okay, I know it's got to be close to this number. It's going to be this number plus some little bit. Okay? So what we're going to be doing here is we're going to be comparing delta y to dy. Okay? So here's my function. Okay? Y equals x cubed. So let's find delta y, which is going to be your f of x plus my change in x minus f of x. Okay? Which means this is going to be, my function is x cubed. So this is going to be x, which is 1. They gave it to me right here. Plus my delta x, which is right here, which is 0.1 cubed minus 1 cubed. So this is going to give me my actual change in x. So it's 1.1 cubed minus 1 cubed. Which gives me 0.331. Okay? Now, we're going to find delta y, which is f prime of x dx. Okay? So in this case, f prime of x is going to be 3x squared dx. Then we plug in x, so this is 3 times 1 squared times dx, which is right here, which is 0.1. And so you get 3 times 0.1, which is 0.3. So you can see the difference between delta y and dy is very, very small. And basically, we just did part of our linearization. Okay? Because we know that basically if we were finding the actual change, y at 1 is this 1.1 cubed minus 1. This is the change from 1 to 1.1. This is also an approximated change from 1 to 1.1. Okay, and that's basically what we're doing. All right? So differentials are really kind of easy. You just have to know the notation and what they're trying to find.